So, this is the one existing result. Now, let us see few functions which are always be Riemann integrable functions, like a continuous function. They are always a Riemann integrable functions and some other case. So, let us take the problem various types of the Riemann integrable function. Okay. Various types. So, first theorem is if f is continuous, on a closed interval a b, then f is Riemann stress integral with respect to alpha on a b. This is okay. So, let us see the proof. Alpha is given to be a monotonic functions. So, once it alpha is given to monotonic, alpha is monotonic function either increasing or decreasing defined over the interval a b. So, alpha a, alpha b, these are finite values, okay, alpha n finite values, and now alpha b minus alpha l is a fixed number. So, what let epsilon l greater than 0, let epsilon l greater than 0 be given. Now, since alpha b minus alpha is a finite quantity, so we can identify some eta such that, so choose eta greater than 0 such that alpha b minus alpha a multiplied by eta is less than epsilon. This is possible because these are the fixed value, finite values. So, we can choose the eta to be epsilon over this number, and since it is monotonic either increasing or decreasing. So, it cannot be alpha a equal to alpha b, okay, unless it is a constant function which we are not taking. Okay. So, we get this one less than epsilon. Further, since f is continuous on the closed and compact and closed and bounded interval, this is a closed and bounded. So, every continuous function on a closed and bounded set is all in a compact set is uniformly continuous. So, this shows since f is continuous, so it is uniformly continuous on the interval a b. This one is given. So, apply the definition of uniform continuity. So, there exists. So, for given epsilon l, so for given epsilon l, the same epsilon greater than 0, there exists a delta. There exists delta positive, it does not depend on the point such that the value of this functional value f x minus f t remain less than eta for all x and t in the interval if x belongs to the interval a b, t belongs to the interval a b, and such that mod of x minus t is less than delta. This is by definition of the uniform continuity of the function. So, since f is uniformly continuous, it means if we pick up any 2 points in the interval a b which satisfy this condition that x minus t is less than delta, that is in the delta neighborhood of the point t or any, then images will fall in the eta neighborhood of f t. That is this eta, say I think it is less than epsilon r, this is less than eta will come. Okay, fine. Now, choose the partition P. Now, if P is any partition of the interval a b such that delta x I is less than delta for all I. It means, we are taking the partition a b as x naught less than x 1 less than x 2 and less than x n equal to b. So, here is the point say x I minus 1 x I. Okay. So, this delta x I is x I minus x I minus 1. Now, this delta x I is because we are choosing the partition less than. So, this is positive if the length of this is less than delta for all I. For all I we are there. Now, if we picked up any point inside this delta x I, then what happens? The images functional value at the point x I minus m I, this difference will remain less than eta because of this, because any point x y which is less than lying between this interval x I minus 1 or t I, if this is less, corresponding images will be there. So, the maximum value and the minimum value of the function will also satisfy this condition. If the point is here in the closed interval x I minus 1 and x I and function attains the maximum and minimum value, then they have to follow this result. So, because of f uniform continuous because of uniform continuity of f, we have m I minus small m I is less than or equal to eta for I equal to 1 to up to n. Is it okay? Now, consider this. We want this we want the function is a Riemann Stacy integral. It means, we wanted to use that result that if the upper sum minus lower sum is less than epsilon for some partition, for a given epsilon there exists some partition such that upper sum minus lower sum is less than epsilon, then the function f must be a Riemann Stacy integral. So, let us consider, choose the partition P first and then consider the upper sum of the function f with respect to alpha over this partition P minus lower sum of the function f with respect to this partition. Now, this is by definition is nothing but I equal to 1 to n m I capital M I minus small m I delta alpha I. Is it okay? Now, what is it? This is already given to be less than eta. So, eta and sigma I equal to 1 to n delta alpha I is it nothing but what? This is the value of alpha at the point, means I is 1. So, delta alpha 1 means x alpha x 1 minus alpha x naught plus alpha x 2 minus alpha x. So, all gets cancelled and finally, you are getting to be eta alpha b minus alpha a. But we have chosen the for epsilon, we have taken the eta in such a way that this is less than epsilon. So, this shows, this implies f belongs to the Riemann Stacy integral with respect to alpha, and that is proved the result. So, every continuous function is a Riemann Stacy integral, and in particular every continuous function is a Riemann integrable function. Next shows that is also if f is a monotonic function, f is monotone, if f is monotonic on the closed interval a b, and if alpha is a continuous function, is continuous. Now, apart from this, alpha is also monotone. Remember, this I need not to write, because we are assuming this is already monotone function, but every monotone function need not be continuous throughout. So, here we are assuming exclusively alpha to be a continuous apart from its monotonicity on the closed interval say a b. Then f is Riemann Stacy integral, or f belongs to the class A. Okay. Let us see the proof of this again. So, it means the monotonic functions, if f is monotonic and alpha is continuous, then this will be a Riemann Stacy integral. Now, in case of the Riemann integrable function, alpha x we are choosing already x. So, over the closed interval a b, if we check alpha x equal to x, it is automatically a continuous function and it is a monotonic function. So, basically it satisfies this condition. So, you need not to take this condition when you are dealing with the Riemann integral. What simply say every monotonic functions on a closed interval a b is Riemann integrable function. But in case of this we have to take a condition on alpha as it. Let us see the proof of it. Let epsilon l greater than 0 be given. Then again, because alpha is continuous, so it will resume all the values from alpha a to alpha b, it will resume all values. Therefore, we can partition it delta alpha, we can choose the equal partition alpha b minus alpha a by n as a n partition for this sub partition of the interval a b like this. So, we can choose that. So, for any positive integer, for any positive integer n, for any positive integer n, choose a partition, choose a partition P in such a way such that the alpha b minus alpha a divided by n is our delta alpha I, alpha b minus when I is 1 to n means equal part, delta alpha 1 is the same as delta alpha 2 is the same as this, and the value is alpha b minus, and this is possible since alpha is continuous. If alpha is not continuous, it means that there is some point in between a and b, the function alpha may not be defined at that point. So, we cannot talk about all these things. So, since it is continuous, therefore, all the values in between alpha and alpha b is possible. Therefore, we can divide it and get the equal values of delta alpha I. Okay. Now, suppose f is monotone, this is given f is monotone. So, let f is monotonically increasing function, monotonically increasing function. The similar case when monotonic decreasing function can be proved in a similar way. So, once it is monotonically increasing function, it means when you choose a to b partition as x naught, x 1, x 2, x I minus 1, x I and x n is b, then value of the function at a point x I is greater than the value of the function at a point x I. So, over the interval x I to x I minus 1, the m I, the maximum value of the function will attain at the point x I, while the minimum value will attain at the point x I minus 1, because it is increasing function, monotonically increasing function, and this is true for every I 1 to n. Okay. Now, consider the upper sum of the function f over this partition minus lower sum of the function f with respect to alpha over this partition. Now, this will be equal to what? If you write this thing is sigma I is equal to 1 to n m I minus small m I into delta alpha I, but m I minus small f m I is this one. So, we are taking delta alpha I, we are choosing same, it is independent of I. So, we can take it outside by n, and this sum I is equal to 1 to n, what you are getting is f of x I minus f of x I minus 1, this is the value. Now, this when you substitute I equal to 1 to n, the terms get cancelled and only you get the f b minus f a. So, finally, you are getting alpha b minus alpha a by n f b multiplied by f b minus f a, this you are getting. Now, this one is less than epsilon l, this follows from f b condition is okay. This is a small quantity, alpha b minus alpha a is less than this. Now, this part when you are taking is less than epsilon l given. Why? So, if you are taking this alpha b minus alpha a by n, f b minus f a, and this divide by n. So, n is sufficiently large. Okay. So, we can take this is less than epsilon r as n is taking sufficiently large. If n is taking sufficiently large. Okay. So, when n is sufficiently large, the total thing can be made less than epsilon r. Therefore, it satisfies the condition 1, which is necessary and sufficient condition for a function f to be in the class R alpha. So, this shows f belongs to R alpha. Okay. So, that is what another results which we so, every monotonic functions. Now, we come to the f is bounded function. Suppose f is bounded on a closed interval a b, and f has only finitely many points of discontinuities. On the interval a b, and alpha is continuous at every point, at which f is discontinuous. Then f will be an element of R alpha, that is f will be a Riemann staticity. So, what it shows is a b interval is given, the function is given to be bounded on this, but at a point of say these are the points, this is the point of discontinuities, these are the points of discontinuities of f, but the finite number, these are finite points of discontinuity, not infinite number, it is a finite number of points are there which is a point of discontinuity. And what is given is at these points alpha is at these points alpha is continuous, that is very important part. If alpha is also discontinuous at this point, then this result will not hold, that we will see while proving. We can easily get easily see the reason if both the alpha and f has the same point of discontinuity over the interval a b, then the f cannot be in R alpha. This result will not hold. Only this result hold when the function is discontinuous at the point alpha must be a continuous at that point. So, this is the very important point here to prove. Okay. Let us see the proof of this. Let epsilon greater than 0 be given. Now, since f is bounded, so let us see the supremum value of f x is suppose m. This is the supremum value. Now, let E be the set of points at which f is discontinuous. Okay. Now, since E is finite, because it is given that function f has a finitely many point of discontinuity. So, since set E is finite, so we can cover E by, so we can cover E by means of a finitely many disjoint intervals, by finitely many disjoint intervals say u j b j, finite element disjoint interval which is a subset of A B, because these are what these are the point of discontinuities. So, only a scattered point is isolated points, we can cover it by means of these intervals, okay, like this, say u 1 u j v j, this is the interval covering. Now, since function f is giving to be continuous at this point, so it means by definition of the continuity, if I look that definition of the continuity, what happens? Say this is the okay. So, at this point the function is continuous, it means for a given epsilon greater than 0, if I check say alpha is this point, then at this point alpha, and for any number say epsilon by n, suppose these are n points are there. So, I can choose the epsilon by n say interval length, so that all the points image of any point inside this interval is falling there. So, corresponding to this we can identify a length, a delta neighborhood such that the image will fall. So, some of these values alpha x minus this alpha values at this interval can be made less than epsilon, because of the continuity. So, that is the advantage of alpha taking to be as a continuous at the point where the function has a discontinuity. So, that is what. Okay. So, let us take the difference of them. Now, such that the sum of the corresponding difference is less. Okay. Now, since alpha is continuous at these points, okay, at this point. So, we can, so for a given epsilon, greater than 0, we can choose delta j such that the sum of this, such that the corresponding difference is less than epsilon, such that the sum of the difference corresponding difference alpha v j minus alpha u j is less than epsilon. Let us see why. I will again repeat, suppose this is the, these are the points. So, let this point is covered by this interval u 1 v 1, here we are taking say u 2 v 2, here this is the point, then u 3 v 3 and like this. Alpha is continuous at this point. So, we can for a given epsilon greater than 0, we can identify here delta 1, delta 2 and so on, such that image of this for this epsilon, image of any point will fall within the epsilon neighborhood of this. So, what I am choosing is the total sum of this difference is less than epsilon. It means, if the number is n, then each one we can take epsilon by n. So, the total multiplied by n will give this. So, that is what is getting. Okay. Now, we can replace these intervals in such a way. So, okay. Now, second step what we do is, this is the first step, second step what we do, we can replace, we can place these intervals in such a way, that every point in such a way that every point of E intersection A B lies in the interior of some interval u j v j. What is the meaning of this is, E intersection A B, this is the set of those points say by I, such that f is discontinuous at by I. Okay. So, now you are taking this these points are enclosed by u 1 v 1 in such a way that each point of this lies in the middle of this, in the interior of this. We can take up u 1 v 1 in such a way that the first point lies in y 1 in this, u 2 v 2. So, that the second lies in it and like this. So, this is the way we will construct and then proof will go. So, next time we will continue this proof. Okay. Thank you.